A very good evening and a warm welcome to today's session. My name is Shaunak, and what we would like to do today is that we would like to explore something which is called Poisson's equation. Now, it is a French pronunciation. It is not pronounced as Poisson, but it is Poisson. And just to tell you before we go ahead with today's session, Poisson equation is a very powerful tool. It is a kind, I won't say it is a mathematical tool, but it is a tool for physics. First of all, again, a quick request to every one of you. Is my audio and video clear? I know the video part I can see, but audio part I cannot. So if anyone kind request, if you can please put a comment, yes or no in the chat box, then it will be easy for me to understand. Is the audio part clear particularly? Is my audio clear? Okay, great. So Poisson's equation actually helps us to understand a lot of things. For example, electrostatics, liquid, hydrostatic equilibrium, and a lot of things. But what we would do today is that we would try to explore Poisson equation first. What is the overall meaning? Get a very deep fundamental idea of this equation. And then we will see how gravity, the nature of gravity changes or redefined with Poisson equation. Again, as yesterday we talked about Lagrangian, which is a kind of an extension of Newtonian mechanics, not dealing with individual particles, Poisson equation also deals with something similar, where the notion of Newtonian gravity extends further, and for various other situations, we can deal with that. So without further introduction, let us first start the Poisson equation. Now, this equation actually requires some other areas of physics and mathematics introduction, which I will do one by one. But first of all, I would like to imagine you as this. Now, okay, Fabio Mongillo, want to say thanks for this nice sessions. Absolutely. Great, Fabio. I think you are joining from which part of the world? Please let me know. And I really thank you for joining. You are absolutely welcome. Now, I have drawn the definition or the picture of a bridge. Why it is a bridge? Because Edinburgh, okay, UK, wonderful. Thank you, Fabio, for joining. Wonderful. Now, why I have drawn this bridge? Because I want you to imagine Poisson equation as a mathematical bridge. The left-hand side of the bridge consists of source. Anything in the physics world, we have a source. For example, a mass, a density, charge, heat, whatever. Now, this source actually is created. It actually creates another part of the bridge, the right-hand side. If you see, this is called the potential. So the left-hand side is the root cause. For example, there is a mass which causes gravitational potential. For example, there's a charge which causes electric potential. There's a heat distribution which causes the temperature distribution. So each of the left-hand side of the bridge, the source, has got a right-hand side, which is the potential. So there is a cause and there is an effect. Simple. In mathematics and philosophy also, we come across cause and effect. So Poisson equation is actually a set of partial differential equations, and it acts as a bridge to know where the source lies and what is the effect, in simple words. So it looks like Nabla square F equals to phi, or this or this. These are different ways of writing the Poisson equation, but the basic idea is that there is a source, which is the cause, and there is an effect. To make things simple, think of this particular part, that gravity is the phenomena. That means physically we see gravity. What is the source? Mass or density, and the potential is the gravitational potential. There is electrostatics, a physical phenomena. What is the source? Charge. And what is the potential? Electric potential. Then there is electrostatics. What is the source? Heat. And what is the potential? The potential is F. So each of these things have got a physical phenomena which gets a source and which gets in a potential. Now here you see that the Poisson equation actually serves as a mathematical framework between the source and the potential field. Now I have actually given this in a very general form. This is the most generic form, Nabla squared F equals to phi. Don't worry if you don't understand what is this inverted triangle. I'm going to explain that. But first, let us understand from this part of our session is that F, the F that you see is actually the potential. And this is a scalar function. That means it's a singular number, and it describes the underlying structure and influence of the physical system. The right hand side, you see there is a phi, and phi actually denotes the distribution, the source, which quantifies the physical quantity responsible for generating the potential. For example, mass density in gravity, charge density in electrostatics, and heat distribution in thermal conduction. And this inverted triangle is basically called the Laplacian operator, French mathematician Pierre de Simon du Laplace. But we will come to that. First of all, let us understand that this inverted triangle is the Laplacian operator. So what we understand is that the source acts as the fundamental cause of the phenomena. It represents the physical quantity. The potential acts is a abstract scalar function, that how the source influences, and the field or the gradient or potential observes force field or flow in the system and is derived by taking the gradient of the potential. So you see a source, mass, charge, density, and this source actually creates what is called a spatial variation. Spatial variation can be gravitational potential, whatever, and then there is something which is called the, which generates the field. Now imagine this kind of a scenario. For example, you can have a heavy ball placed on a rubber sheet. Typically in general relativity we see this. So as I have mentioned in the slide, that the heavy ball actually is the source phi, okay, which is the mass density. How much mass is concentrated, that is the phi, okay. The rubber sheet presents the dent, that means there is a curvature, which is the potential field. And deeper is the curvature. This is a heavy ball, you can place a lighter ball. Deeper is the curvature, stronger is the gravitational potential. So what this equation tells, all in all, is that if we place a heavy ball on a rubber sheet that curves around, the heavier the mass, the steeper and deeper is the curvature. And in simple terms, we can say mass bends space, and the Poisson equation tells us how much bending happens at each point of time. Now, this seems to be very simple. I mean to say, we all know this, isn't it? That if you put on a heavy ball, it would cause a change. But measurement of this creates a problem. So, and this is a very generic equation. Poisson equation is a very generic equation, and it can be extended. So what you can see from the left-hand side of the equation, now I will show you the overall idea. You see this one. What you can see from here, that the left-hand side tells how the field is curved. Now here there is gravity, it can be electrostatic, liquid, whatever, but overall the curvature or what happens on the field is the left hand side. And the right hand side tells what is curving the field. That means the source. So we can say the Poisson equation tells us that space bends where mass or where there is mass or charge. So you can say that Poisson equation describes how matter, charge, or energy, anything bends the geometry of the space. Its left-hand side is how the field is curved, and the right-hand side, what is curving it. So whether it is gravity, electricity, or heat, Poisson equation actually hides beneath the surface. It shapes the universe, and that is how the equation tells it. Mayur, I have already, it's a very good question. I have already started making a video on divergence and curl. Yes, it is a very div, grad, and curl. And I will cover that in today's session also. Just be there. It won't be a very long session, but it will be a very fruitful and effective session. Okay. Now here you see what I was trying to tell. The left-hand side, can you please recommend a book for studying classical mechanics from basic? Yes, I will do that. Waji, what you need to do is that you can WhatsApp me or you can email me. I will send you, because if I start now talking of the book, the session will be disturbed. So please contact me later. I think another person also contact me in WhatsApp. I was taking a little bit rest in the afternoon. I will send all the details in email. Definitely, no problem. So as you can see, the left-hand side of the equation talks of the geometry and the right-hand side is the source. Same thing happens with Einstein field equations, where we see the same thing. That is, the left-hand side is basically the source or the curvature, and the right-hand side is the T mu nu, that is the source, and the left-hand side is the geometry. So From here, what we can tell, this slide is pretty important, because from here what we can say is that why Poisson equation under weak field approximation comes back to Einstein field equation. This slide tells you that the left hand side is basically the source. In Einstein field equation it is the curvature, and the right hand side is basically the left hand side is the geometry, that is in Einstein field equation the curvature, okay, as we have seen the ball, etc. And the right hand side is the source, that is what causes the curvature. Same thing happens in Einstein field equation. That is why, for a deeper understanding of gravity, classical gravity, this is very important. Okay, now what we have seen till now is the overall idea of Poisson equation. Now, as I was telling, that Poisson equation is really something very interesting and very deep. It contains various other forms. I won't go deep, I will just go through this form. Now here you can see this is Poisson equation of gravity, which we say. So the here you can easily understand what it is, so I won't go much deep in this. Here you can see that yes, so here you can see that there is a field which is causing the curvature, the Laplacian operator. There is a gravitational potential, which is the phi. There is a minus sign. Don't worry, I will come to this minus sign. One thing, yes, you have guessed it rightly, that because gravity attracts, pulls things, do not pushes things apart. But remember, this is again classical gravity. If you take the Big Bang and the cosmology, then you will see Einstein's gravity tells that it can repulse, it can push things apart. But here only gravity is attracting. So that is why it is negative. Okay. G is the gravitational constant. 4 pi actually comes from a symmetry of a curvature, a spherical part. We will come that later. And rho is basically the mass density. So what happens is that, as I was telling, that it relates the gravitational field to the mass density. In simpler terms, where there is more mass, there is more curvature. So the left hand side is actually the curvature and the right hand side is the potential. And the negative sign shows that gravity is always attractive, but it not pushes, as far as Newtonian mechanics is concerned. Now you see another interesting part. This is called Poisson equation in electrostatic. Now V, you can see, I will just explain one by one slowly, you can understand. V in the equation is the electric potential. That means the energy per unit charge. Energy per unit charge in any point in space. Nabla square V, this inverted triangle, it is the Laplacian operator. This tells how electric potential changes from space to space, right? Okay, the right hand side, you see again there is a negative sign. This is crucial because it indicates that positive charge density creates a negative curvature in the electric potential. And also, I would like to say you, what if gravity deviates from Newton's law, and what are possible change in Poisson equation? Yes, that is exactly, Bhima Raju, what the Einstein field equation talks. Gravity does not deviate from Newton's law, but in curved space-time, Newton's law doesn't happen, and where the Poisson equation or the Einstein field equation comes in play. And this is exactly, Bhima Raju, we are going to explain today. So just hold on, we will just try to answer your question. Okay, first let me tell of this. Now, this negative sign, which I was telling, that this actually tells that why positive charges repel and minus and plus charges attract. This is the negative sign. Okay, it indicates basically that charge density creates a negative curvature in the electric potential. Rho, you already understand, it is basically the charge density, and this is the permittivity of free space. Okay, this is the fundamental constant. That means it represents how much the ability to vacuum to permit electric fields. This is called the permittivity in free space. So let us now understand that the V decreases as you move closer to the positive charge. Now, the electric field, as you know, always points from higher to lower potential, and that is the reason electric fields go outwards from positive charge and inwards to a negative charge. Can you see this one? The blue one is the positive charge. Okay, things are going outwards. And in the red one, this is the negative charge, and the arrows are pointing towards. And this is the reason. Because electric fields moves from higher to lower potential, electric fields go outwards from positive charge and inwards to a negative charge. And the negative sign actually ensures that positive charges create attractive potential. So overall, what we can tell of this equation, it establishes a relationship between the electrical potential V and the charge density rho. And it also states that the Laplacian of the electric potential, which you can see this inverted square V, is directly proportional to the negative of the charge density divided by the permittivity of free space. In simple terms, let me summarize this. The charge density acts as the source that creates the potential, and the Laplacian of the electric potential describes how electric potential is curved or distributed in space due to the presence of the charge density. As simple as that. There is another thing which we use in fluid mechanics. This is also here. You can see P is the pressure field, rho is the source, and nabla square again is the same, how the pressure curves or spreads across space. So what the equation tells is that the nabla square P tells how pressure bends or curves. The minus rho tells what is creating the pressure. So now here is the difference. You see that in electrostatic, the source pushes the field away, the potential drops near positive charge. But in fluid mechanics, the negative sign means that the source compresses the space and higher density makes pressure drop around it. Now this is something negative. As you can see here, that on the left hand side of the slide, you can see that it pushes the field away. But here in fluid, the source actually compresses and higher density makes pressure drop around. So this is the difference. In electrostatic, the source pushes away. In fluid mechanics, it compresses. So in here, what does the negative sign doing? You can answer to this question. So if rho is greater than 0, there is more mass or more heat, for example, and the pressure goes down. So you can see the blue arrow or the sign I have put, it is going down. And if rho is less than 0, that means it is a cold region, so pressure is going up. So what we can say that in electrostatics, repulsion means charges pushing away. Fluid mechanics, compression, higher density, and in gravity, attraction means space bends naturally with a negative sign. Okay, so here is a quick summary of everything which you can understand. Here you can see these are the different forms. One, we have studied gravity, one we have studied electrostatic, then we have studied fluid mechanics, and we have studied what is called heat mechanics. Heat mechanics I have not explained, but anyway, you can very well understand what it means. So always remember that the left hand side shows how the field is curved, and the right hand side shows what is causing the field, and Poisson equation actually measures this. Just give me a sec, I will just have a glass of water. Okay, so I hope today's session is going fine. You're all enjoying. Now, all this takes down to the next part of our session is what is this nabla squared? I mean to say what this triangle, inverted triangle looks like. Okay, if I go a little bit by the history, then actually you can see this nabla or del is actually resembling an inverted Greek delta, which comes from the symbol of a Hellenistic Greek word, which is a Phoenician harp. Okay, here you can see that the harp is also inverted. So in the nabla sign is also inverted. So what we can say is that you can think that this inverted triangle actually acts on scalar or vector fields or any other fields. It can be any other fields, and it produces different types of derivatives. So that is why it is called a differential operator. Nothing to get confused about. Differential operator means any kind of an operator that performs differentiation. It would have been an integral operator, it would have been any operator, right? So that means it actually performs differentiation in multiple dimensions. So you can think of it as a vector that contain partial derivatives. Don't worry if you don't understand partial derivative. I will make you explain it with a simple analogy. Dx by dx, d by dy, and d by dz. So each of these measures how quickly certain quantity changes over a small distance in x direction, y direction, and z direction. So you can think of this as a hill. I have drawn this diagram. You can think this of a hill. If the road is steeply uphill, then partial f by partial x is positive. If the road is flat, partial f by partial x is negative 0. And if the road is downhill, then it is negative. Okay, I will now give you a very, very simple example, an analogy which I have used, and I will just make you understand about this. Now, I want, just a second. Now, I want you to imagine a packet of sugar. Okay, you see this one. Now, when you spill open the sugar, for example, you just throw it open, you cut open the sugar, you will see that lots of sugar spill over, but lots of sugar at the origin and less as we get away from the origin. So you can see the left hand side of the sugar is less, the right hand side of the sugar is less, and the central part is more. Okay, and what we can say from here is that if we calculate, say for example, our sugar distribution as f, for example, the sugar distribution is f, the upward arrow. Okay, and if you want to find df by dx, that means it simply measures how quickly the sugar distribution changes as we move along the x direction, and we can think of it as measuring the gradient of, or the slope of our sugar distribution. Here you can see what happens is that df by dx equals to 20. That means the slope is very steep, and df by dx is 5, where the slope is a little bit flatter. Okay, so df by dx actually tells how quickly the sugar distribution changes in the x direction, and df by dy tells how the sugar distribution changes in the y direction. Now, this is quite simple. But what would happen if the sugar distribution is not only changing in x and y direction, but in some other direction? So this is an example. Think that the sugar distribution is changing in not only in x and y, but in some other direction. Okay, so the gradient or the steep, so our sugar distribution drops off quickly. Whereas in other area, the gradient, as you can see, is not steep. That means the sugar distribution is not changing the amount. So all this partial f, partial x, partial y actually tells that how much the sugar distribution is changing, corresponding to x direction, keeping y and z same, again y direction keeping x and z same, and again the z direction keeping x and y same. Now, you might say that why we are doing this partial differential, because Poisson equation or further equations that we will see doesn't only happen in x and y direction. It will happen in different directions. In gravity also, it will take different directions. So general ODEs, or the ordinary differential equations, won't work. So first imagine that the sugar distribution here, when you spill over, how it changes. Then we measure the sugar distribution. Wherever it is high, it has got a high gradient. Wherever it is slow. But now what we are doing is that we are measuring the sugar distribution not only in x and y, but in different direction. So you can think, I would say, the curly D's are basically isolating the change in one direction. So here it is. df and dx measure the gradient in the x direction, keeping y and z constant. Again, partial f by partial y means changing the gradient in the y direction, keeping the gradient x and y and z same. Sorry, this should be x. I'm so sorry. It should be x. So one direction is changing, others are constant. One direction is changing, others are constant. Okay. So here is the catch. Here is the catch. So what I want you is that take this as, you can think of this curly D's are isolating a change in one direction without worrying about the change in other direction. These are called partial derivatives. So separates change in x, separates change in y, separates change in z direction. Okay. So this is how it happens. But note one thing, with in the Poisson equation, we noticed what is called a nabla dot. So nabla dot means we have a del squared. So that means, as I have written over here, you can understand this is del dot del. That means it is basically, those who know, it is a dot product between two vectors. Okay, del dot del, dot product between one vector and the another. Now, if you are aware, somebody was telling me just now, who was that? Mayur. Yes, he is very right. Now, if you are aware about what we call the divergence, gradient, and curl, what we are trying to find is the divergence of the gradient of some quantity. So as you can see here, what I have written is that the dot product of the scalar dot product or the scalar product is basically two vectors given multiplying by corresponding components of these two vectors and then adding up these vectors. So if you have two vectors, a sub x, a sub y, a sub z, and b sub x, b sub y, b sub z, then you take the dot product a dot b as a dot x bx plus a y by, a z bz, and it can go on and on and on. Why gradient of a scalar is a vector quantity? Because it has got a magnitude as well as a direction. Right? This can have a better explanation, but right at this moment, Bhima Raju, I think you can go a little bit on the basic physics. You will understand. Gradient is scalar because gradient of a scalar is a vector quantity because it gives the amount of magnitude and the direction of both. Okay. So here you can see that the components of these two, I know Bhima Raju, I have not answered you properly, but again, I have to go back and explain, which I won't do right now. So you can come back to me, I will do. So what we understand is that the dot product or the scalar product between two vectors is given by multiplying. Now, as we have added up a dot x plus b dot x, ay, by, same way, in the same way, that the way we have added all the components of the a vector and b vector dot product, we do the same thing when we are trying to find out the dot product between these two del vectors. What are the two del vectors? Nabla and nabla. Two dot, nabla dot, nabla dot. So when we are trying to find out the dot product between these del vectors, we do everything, but what we do is not multiply, rather we are applying a partial derivative over a partial derivative. So you can see right at the bottom, partial x, partial y, partial z, dot, that means multiplied by partial x, partial y, partial z. And this actually gives partial by partial x, partial by partial x, plus partial y, etc. And this would actually show why can't we take divergence of a vector? I will answer to those questions a little bit later. First, let me complete the agenda which I am. Okay, so here you can see, I will just pause and you can have a look on it. Can you see this? Is it all clear? The question what Waji asked is that why can't we take the divergence? We can take the divergence of a vector, but there are certain conditions that divergence is defined that should be a scalar function, right? And the divergence should measure the outflow of a field. So just to tell you in short, Waji, you cannot take the divergence of a single vector. The reason is that divergence requires a vector field that varies with position. So for a proper vector field, the divergence is well defined. So you need to have basically a divergence as a scalar function, and then you can have the divergence measures the outflow of a field. So because the divergence requires a vector field which varies, that is why for a proper vector field, the divergence is well defined and useful in physics. But under certain conditions, you can take the divergence of a vector. Okay. Great, wonderful. Okay, so now you can see what I have done is that I have just taken the derivative over the derivative over the derivative, and you can write using the partial derivative in this manner, which gives you the value. So you get the partial square by partial, etc. Now we come to the central part of this part. So till now what we have understood, what is partial derivative, why this del dot squared happened. Right? Why this del dot squared happened, you can take it from here. Just like adding up or multiplying, taking the dot product of two vectors, we have taken the dot product of one nabla vector with the another, and we get the nabla square. Now, definitely there is a name, right? What is this nabla squared called? Although I have told this name earlier, this is what is called a Laplacian. Okay. Now, Laplacian is nothing, what we have explained is simply the dot product of two nabla operators. So nabla dot nabla is nabla squared or nabla squared f. This is basically what is called the Laplacian. So actually what we say, this actually leads to vector calculus. Divergence measures how much a vector field is spread out. Here you can see I have given that it is a positive divergence where the arrows are moving out. Okay, that means that the vector field is spreading out from the point, like water flowing from a source, etc. Okay, or you can imagine air flowing from a fan. Then you have got a negative divergence, which tells that vector field converging, like water flowing into a drain or air getting sucked into a vacuum cleaner. And then there is zero divergence. When divergence is zero, that means the amount of flow entering and leaving the point is equal. There is no net flow. Okay. For example, a constant airflow. So in short, what I can say is that a positive source, a negative source, sink, and zero means no source or balanced flow. So here you can see that nabla f is the gradient. This tells how quickly the field changes. That is the first derivative. And nabla dot nabla f, this takes the divergence of the gradient, which is basically measuring how much the field bends, curves at each point, which is basically the second derivative. Now, in order to give you a better example, I will just tell you that is the div grad divergence of the gradient, right? Here is a nice example. I want you to imagine a room which has got a temperature, okay? And these are pointed by X, Y, and Z coordinates. So the gradient nabla f is telling in which direction the temperature is rising, okay? And nabla dot nabla f, that is the Laplacian, is telling how much the heat is piling up or whether it is escaping at any point. So at the bottom, you can see there is a picture of a mountain. So what I'm trying to tell is those arrows which are pointing away from you in all directions. That means divergence is positive. Nature is saying that something is pushing out here. Okay, for example, a hot iron ball or positive electric charge. So this is what actually this tells, that you're standing in a valley and the field is trying to escape from here. Now you see this picture. This is also very nice. What is happening over here? If you're on the top of a hill, then the arrows are pointing towards you. Okay, then something is sucking in, everything getting inside. This is called the divergence is negative. For example, I will show you what do we mean by that. So overall, and when you're starting on a static or a flat land, it is no divergence. So what we can say that nabla squared f equal to 0 means flat. If it is equal to phi, then there is some amount, which is a Poisson equation, etc. And the first nabla f tells how fast in and which direction the field is changing, and nabla dot tells how much something is spreading out on a point. Okay, I will give you another very quick example. Imagine this one. Okay, so here what you can see. Here you can see there is a hot iron ball. The field is spreading out. So the point surrounding the hot iron ball is by a higher values. Heat or mass is flowing outwards. Ice cube, the field is pulling in. The point is surrounded by lower values. Heat or mass is flowing in. And when there is no net flow or equilibrium, the surface is rather valley nor a hill. So what we can say that positive divergence is like standing inside a valley where everything is trying to run away from you. Negative divergence is like standing on a hilltop where everything is trying to pull you in. And where there is no divergence, the landscape is perfectly flat, and you can see that the nature is in balance. So I just thought to give you a few examples. This is the divergence, which I think somebody was telling, Mayur, now you have got an understanding of the divergence. Your gradient and curl, we are not covering here. Curl we will do. Okay. Now, in this part of the video, we have come just at the middle. Now we are entering the most important part of our session. Till now, we had looked into what is called a very generic look at Poisson equation. Okay. I mean to say you can use this in electrostatic, liquid flow, you can use in gravity, everywhere. But what about a specific type of equation? And this one, which you can see, this one, which I'm going to explain. And first, I'm going to go get a little bit background, and then I will tell you why this is important in understanding what is called the Poisson equation. What you see right at the bottom is a famous theorem or a famous equation, which is called Gauss's law of gravity. Now, again, you might have a question that why do we need a Gauss's law of gravity? Newton's law are serving very well. But again, the same point. There are point particles. If the point particles are more, if you're taking gravity of a particular field or a long region, then this Newton's F equals to gm m1 m2 by r squared won't work. So what do we need is this one, a genius born during early days. And I think he started understanding mathematics before learning even the language, German language. So his name is Carl Friedrich Gauss, is known as the Prince of Mathematics. Okay. Now, the next slide, what I'm going to show, before that, a note of caution. There are many things in this slide. Don't go everything, just go by my words. First of all, concentrate on the extreme left-hand side. These are different forms of Gauss's law of gravity. Sometimes it is written this or this or this or this. Okay, forget those things. Now concentrate on the middle part of the of your screen, where there are all those red circles, etc. I will just explain you one by one. Now, first of all, let us understand that integral sign with a circle at this bottom, at the middle. Now, the integral sign with a circle actually shows that the surface is closed. Now, you might say, why it is closed? There are many reasons. We are not taking an open surface. There are many reasons for that. Currently, for electrostatics, etc., Maxwell's equation, we take a closed surface, right? So, first of all, understand that surface is closed like a sphere. Okay, so the integral, what it does, it calculates the total gravitational field through the entire surface, which is this S. S is the surface. Okay, that means in simple words, you can say how much the gravitational field is flowing out from the enclosed mass. How much the gravitational field is flowing out. That is this integral with a circle, and S is denoting. Now come to the G1. This is known as the gravitational field. Now, it is not the gravitation and acceleration, right? It represents the gravitation and acceleration, but it is the gravitational field. That means at each point in space, due to mass distribution, it is a vector field that points towards the source of gravity. We should say G equals to minus nabla V, which I have not shown over here, but I should have shown. My kind apologies for that. Okay. New member. Okay. Okay. Thank you. Okay. These are all good examples to tackle the topic from a different point of view, making it easier to understand. Okay. Thank you. Thank you very much. Okay. Let me continue with this, please. Then I think everybody will enjoy. And thank you, Fabio, for being the new member. Okay. So you understand G represents the total gravitation. There is a dot. Okay. You are only concentrating on the right-hand side. So there is a dot. What is that dot? Dot is the dot product. We know what is a dot product. Okay. Now concentrate on dA. You can say it is called a differential area. Don't worry, I will tell you what is dA. I will show you what it is. So symbol dA, understand that it represents an infinitesimal small vector area element of the closed surface S. So the magnitude of dA is a small surface area, any area dA. And the direction of dA is always outwards, perpendicular. I will show you that. Okay. Negative sign, you all understand. It is gravitational fields are always attractive. So what we tell from here is that gravity always pulls mass inwards, never pushes, as far as classical physics is concerned. And the gravitational field G always points towards the mass creating the field. I will give you a pictorial representation. Okay. So the dot product G dot dA gives the flux of the gravitational field. That means the quantity represents flux, means how much gravitational field passes through the infinitesimal small surface area dA. So integral S G dot dA, this is the total gravitational field. Okay. And the integral is actually calculating the total gravitational flux, the total gravitational flow through the entire surface S. And it measures how much gravitational field is flowing out from the enclosed mass. So all in all, we can say Gauss's law of gravity. Okay, I will show you here the summary is. Gauss's law of gravity, what does it tell? It tells that the total gravitational flux through any closed surface is proportional to the total mass enclosed within the surface. This is the equation, okay? Because mathematicians cannot write good English. No, we can write good English, definitely. So we have put it in a simple English that the total gravitational flux through the closed surface is proportional to the total mass which is enclosed. Now, why I am talking of Gauss's law, you will understand now. You see that we are not dealing with individual particles radial direction, mass 1, mass 2, but we are talking of it as a whole, the total gravitational field, total flow of a surface area. Clear? So that is why Poisson equation and these things come in place. Now, we all know that the Earth's gravitational fields look something like this. We all agree to that? Is also integral with circle called contour integral. Very good question, very good question, very good question. It is called contour integral in some cases, yes, you are right, but in general when we are talking of calculating physics or any flow, Fabio, it actually means basically the integral of a closed surface area. Contour integral in some places, yes, you are very right, it is also mentioned. Yeah, it is true. Okay. Now, do you agree to this, that we know that the Earth's gravitational field looks like this? These are arrows which are pointing towards this. Okay. I mean to say, in this direction, in this direction, in this direction. Okay. I should have had a whiteboard here. I don't have the arrangement. I'm trying to make it happen. Anyway, so it means that if you take this mass, can you see the blue mass on the extreme left hand side? There's the blue box. Can everybody see that blue box? The blue box where the Earth is written with an arrow. Can everybody see this? So if I place any mass, for example, any mass at any of these points, it will accelerate towards the center of the Earth. This blue one will actually, thank you, it actually will come towards the surface of that. Now the question that Gauss's law or we asked is that how do we know? How do we know that the Earth, the gravitational field of the Earth is radially pointing towards the center and any mass will accelerate? How do we know? So for that, I want you to consider the right hand side of the of your screen. You can see the blue dot where the Earth is placed. I have taken it as any random surface. Okay, this is any random surface, the blue dotted one, and we have actually we have taken the Earth or a sphere. Now you can see the blue one, the yellow ones, the small blue yellow circles. You can see that these are the dA. That means we are breaking up this surface into tiny small yellow pieces, and each one of them suppose have an area dA. Now concentrate on the extreme right hand side of your screen. We also represent that dA with a vector. Now, instead of representing an area, then calculating the area, we are assuming that this vector, the vector is perpendicular to the surface or maybe surfaces, because we have many yellow boxes. Okay. So here is a vector which is perpendicular to the surface. And instead of the surface, we have a vector, and the size of the vector is corresponding to the area of the surface. dA, the black one, which is pointing outwards. Okay, the outwards which is pointing. So what I'm trying to make, things easy, that this vector is perpendicular to the surface. Instead of the surface, we can represent it by a vector, and this gives an advantage of representing the surface with just one single vector rather than many vectors. I will show you the next part. Here it is. G pointing downwards, dA pointing outwards, all of this. So in order to find the dot product G dot dA, we consider the gravitational field and the area vectors. These are all the area vectors. This dA, which I have divided into small yellow pieces, now I am pointing it as upwards in a magnified way. Just a second. Just hold on. Okay, so this actually what we are doing is that we are pointing it outwards in this fashion. So this is just in order to magnify and show it. Now we come to the last part of our understanding. Here you can see, when I take this part of the slide, here you see a little bit cumbersome. Just hear me out what I'm trying to tell. So here you can see that the gravitational fields lines align with the area vector, or how much gravitational fields line pass through those area elements. Okay, G dot dA. So I have just again repeated that in order to find the dot product of those little areas and then add up to find out what is going on in our closed surface. So what happens is that here the dot product tells how the two vectors align with each other. So if A dot B is maximum, they are pointing in the same direction. If A dot B is 0, that means they are perpendicular to each other. So it tells that how well the gravitational field align with the area vector. Okay, so as Fabio was telling contour integral, and now remember he is very right, and this also tells that how much closed surface it is. Okay, so M is the central of the mass. But here is a problem which I'm just skipping part because this is a little bit more tricky. Finding a solution, if you want to find a solution for Gauss's law of gravity, it is very difficult. Now, why it is difficult? Because it has got a lot of partial differential equations. It has got a nonlinear nature because the nature of gravity is nonlinear. So that is why we cannot actually find out. I mean to say, again, it is not impossible, but definitely we can find out, but it is difficult. Now, why it is difficult, I have explained, because mass distribution is irregular. There are multiple masses at different locations, and you have to solve the curved space-time, which becomes very difficult. And when it is easy, if you have got a spherically symmetry, cylindrical symmetrical, or plane symmetry. Okay, that is why we cannot find out the perfect or the exact solution of Gauss's law of gravity. But what we can tell from here is that the Gauss's law of gravity, whatever it tells, in spite of all the difficulties and the problems, what we can say is that the gravitational field across the closed surface looks something like this. So you take any kind of an area, you take a curved area, you take a curly area, whatever, it will always show that the arrows of the earth are pointing towards this. Classically, it will point towards this. So that is why Gauss's law of gravity is important, and why all those integral, etc. Because you can take any irregular surface, the solution, although they are difficult, it will show the same one. The earth and things are pointing downwards. Okay. Now, lastly, what I would like to say you is that, as you can see that I have pointed this negative part, this minus sign, there is a divergence where there's a minus sign, and this minus sign actually tells that the area elements have element out of the area. You can see those the yellow boxes and the DAs which are pointing outwards. So if the lines of the earth are pointing inwards, the differential areas are pointing outwards, and that is why it is negative. So the arrows are pointing in this direction. The yellow arrows you can see here are pointing upward direction. So it is negative, positive, negative. That is why it is also negative. So the Gauss's law of gravity, what it gives is that it helps us to find the gravitational field generated by a mass distribution, and it tells that the total mass enclosed within a region, and it equates it to the divergence of the gravitational field, more or less whatever we have shown. Now, the last two slides are very important, a little bit tricky. Here you can see that this is actually the differential form of Gauss's law. Now, as in Maxwell's equation, I hope you all know that Maxwell's equation have two forms, positive and negative, differential and integral. In Gauss's law of gravity also, we have got a positive, we have got an integral form, and we have got what is called a differential form. Now, what we have taken here, it is the differential form. Okay. Now, in this differential form, you can see nabla. We already know this is the divergence, and G is the gravitational field. So here, the divergence of G is minus 4 pi G rho, right? Where rho is basically the mass density. And you see that this equation looks similar to the Poisson equation, because in the Poisson equation also we got some kind of a function on the right hand side, but the only difference is that we have got a divergence of some vector quantity. Here we have got a Laplacian of a scalar function. That is the only difference. Now, understand one thing. This would again require a little bit of explanation, which I'm not doing. Gravity as a force is a conservative force. Remember, gravitational force is a conservative force. What does it mean? It means that the work done by the force to move an object from one point to another point depends only on the initial and final position, not on the path taken. So concentrate on the right hand side, extreme right hand side of the screen. You can see this orange colored circles, right? And there is an arrow. So what I have tried to demonstrate with this orange colored arrow and the red arrow that is pointing is that if we take a simple terms, if we take a mass, those orange circles, and if we move an object in a gravitational field and again try to bring it back to the starting point, the total work done is always zero. Again, if you move an object in a gravitational field and bring it back to the starting point, the total work done is always zero. No energy is lost. That is why we say that work done by a force to move an object from another point are initial and final position, not the path taken. And that actually means that the gravitational fields line are always point radially towards the mass. There is no swirling or no vortex. There's a term called a vortex. That means it goes around. Gravity only pulls, but it never twists. But actually it twists in case of Einstein field equation or general relativity. Here it does not twist. And now you can concentrate on the middle part of your screen where I have actually given, it actually translates to the fact that the curls of the gravitational field is zero. The curls of the gravitational field is zero. That means gravitational field doesn't have a curl. So that is why at the beginning, at the center of the of your screen, I have given the curl of a vector field checks whether the field has got any rotation. The gravitational fields are always pointing radially towards the mass. That means the curl of the vector field is zero. Now, taking this fact onwards, what we do is that if we try to, now you see gradient, that nabla f. This nabla f is what? The curl of the gradient field is zero. So the formal statement is the curl, that is nabla times nabla f is the curl and the gradient. So nabla times nabla f is the nabla squared f. So nabla f gives the direction, that is the steepest ascent of the scalar field, and curls measures how much the vector field twists or rotates. So why does gravity twist in relativity? Newtonian mechanics, the gravitational field is purely central. That means no force can actually, only pulls straight towards the mass. But in general relativity, gravity is not just a force, it is a curvature of space-time. And you can very well understand from here that if it is a curvature of space-time, then that space-time can also twist. It can also bend. That is why we use a lot of differential geometry and topology in curved space-time. Okay, so in Newtonian mechanics, curl of the gravitational field is zero. But remember, in general relativity, because it is a bending of the curvature of space-time, that is why we get a twisting factor. Here we are ignoring the twisting factor. So it is quite clear. So we can write nabla dot nabla f v equals to 0, right? Here we are actually substituting v because it is a scalar field. Because the curl of a gravitational field is 0, we can write that gravitational field as the gradient of a scalar field, g equals to nabla v. This brings us to this part, and this is the last slide of our session today. Here you can see, if we go back to Gauss's law and just substitute, what we are doing is that we are just substituting the Gauss's law and grad v for the gravitational field g. So you see, we know from this earlier, go back to the earlier part, you will understand. Here, g is equal to nabla v and v is the scalar field. So I'm just substituting g equals to nabla v in that dot g part. Okay, and what we get is this equals to 4 minus 4 pi g rho. But we also have to remember, here we also have to remember that nabla dot nabla is equal to nabla squared. So substituting the value nabla dot nabla square equals to minus 4 pi g rho, and if you substitute nabla square here and v is already there, what we get is minus 4 pi g rho. And this is actually the Poisson equation for gravitation, and the bottom at the end what you see, nabla square f equals to phi, this is the general form of Poisson equation. So that is the end of our today's session. So I hope you have really enjoyed. And what we got from here are many things. We understood what is a Poisson equation, right? We understood what is a Poisson equation first. We understood that what is a source, what is a potential. We also understood that Poisson equation can be used in different other forms: gravity, electrostatic, fluid mechanics, etc. We also understood what is a Laplacian, isn't it? We understood what is the gradient, positive, negative, and zero. We also understood what is called the curl of a the gradient of a field. Then we understood Gauss's law of gravity and the significant. This was a fantastic lesson. Thank you very much. So we also understood from Gauss's law of gravity that given any arbitrary surface, the total gravitational inflow is equal in proportional to the outflow. That is what it is. It was an amazing session. Thank you for simplifying the topic. You're absolutely welcome. Then we saw why this Gauss's law of gravity is important. It can occur for any arbitrary surface. And then if we take those surfaces, and as because we know that gravitational field is a conservative force, we get that the curl of the gradient field is zero. Substituting, what we get is basically the Poisson equation. So thank you very much, everybody, for joining. Don't forget to join just 2 hours from now on my other channel, General Relativity Explained, where there is an amazing podcast happening on black holes and singularity. As a very young person, a person who has done a lot of research on these areas, is also what we say a digital creator will be coming, and there will be a podcast starting 8 p.m. India Standard Time. The Fabio is joining from England, Edinburgh, so it is just 2 hours from there. Waji is telling thank you very much. Goodbye, and we'll see you soon in 2 hours from now, and take care.